Okay, hi everyone. So today we have Sutirtha Sengupta from UC Santa Cruz, and he's going to tell us about the effect of rotation on fingering convection in astrophysical environments.
Hi, good afternoon everyone, and thanks for coming for this talk. And I am coming from UC Santa Cruz in the Department of Applied Mathematics, where I do my graduate work with Pascal Garot, who does mostly 3D hydrodynamical simulations of processes that are of relevant to different environments, such as astrophysical and geophysical fluid dynamics. So the topic of my PhD work mainly involves studying the effect of rotation on various instabilities that occur in many different contexts, such as stellar interiors as well as planetary atmospheres. And today I will talk about the primary project of my PhD thesis, which is the effect of rotation on fingering convection and its application in various astrophysical contexts. So I'll just start with pointing out, if it is not very familiar to the audience here, is that what I'm talking about is not the typical kind of convection that people think about in the context of astrophysical fluid dynamics, which is the typical what we call overturning convection, and that is when fluid is unstable according to the Ledoux criterion, which is written here. And in terms of density, it's just that the density gradient with respect to pressure is less than the adiabatic pressure density gradient. But the focus of my talk is another class of convection that is known as fingering convection, which is actually occurring in environments which is stable according to the standard Ledoux criterion. So it is, but it is unstable according to the compositionally. So the compositional gradient, which is defined typically in the same way as the pressure gradient, is negative, which makes the fluid parcel unstable. And this is illustrated in this toy cartoon, which I stole from my advisor's annual review paper on fingering convection this year. And it illustrates a small blob of parcel that is in this configuration where we have more concentration fluid on the top of lighter concentration fluid, and if you move this parcel down, it becomes unstable, because in a typical setting like this, there is a difference between the compositional and the thermal diffusivities of the fluid, and that makes it denser in this environment, and that's why it continues to sink. So this is the basic mechanism that goes behind this compositional convection, which we call as fingering convection. And this has been studied and can be also be demonstrated very easily in a laboratory setting, where you typically have salty water on top of clear fresh water here, and you immediately get this onset of this typical finger-like structures protruding from the salty water to the fresh water. And it is just illustrated with the help of ink here in this cartoon stolen from this review paper.
In this case, in the experiment that you showed, how is it different from the Rayleigh-Taylor instability?
So if you make this sufficiently dense, then you get the onset of the Rayleigh-Taylor instability. But the density gradient between this and this is negligible. It's only the composition that is significantly different. So the composition is triggering this instability, but the Rayleigh-Taylor instability is typically triggered by the density contrast between the fluids. In fact, my second part of my PhD work is to study the effect of rotation on Rayleigh-Taylor instabilities, and that is also in a very similar framework of what we do for the fingering case. This fingering convection comes in the broader domain of the study of double diffusive instabilities, and as I briefly pointed, this is double diffusion, as the name suggests, occurs due to a difference in the diffusivities of two competing gradients that contribute to the density stratification. So in typical context of astrophysics, it's usually temperature and composition that are either stably or unstably stratified, and there accordingly you get these two regimes of double diffusive instability, the so-called oscillatory regime, where the fluid blob just oscillates due to this instability, and this is commonly known as semi-convection, for example, in stellar physics. But I will be mostly concentrating on fingering convection, which happens when the slower diffuser, which is composition, is unstably stratified, as I illustrated in terms of the composition gradient, and the faster diffuser, which is temperature, is stably stratified. And this is the key difference from convection, thermal convection, where there is a thermal instability that triggers the convection, where in this case there's the compositional instability. So this double diffusion is studied parametrically in terms of this diffusivity ratio, and for the case of fingering convection, you have these two diffusivities, which are the compositional diffusivity and the thermal diffusivity, and typically, for example, in stellar radius, these are very different. So these are orders of magnitude difference, where the thermal diffusion is much, much faster than the compositional diffusion. And so in stellar interiors, for example, you get a very small number for this diffusivity ratio, typically of the order of 10 to the power minus 6 or so, which is of the order of the Prandtl number, which I'll define in a bit. And the regime of this instability of fingering convection is defined in terms of the density ratio, which I think I mentioned in the previous slide, yeah, which is just the ratio of the two gradients of thermal and composition. So the regime of fingering convection is between these two limits, and this is illustrated in this cartoon, where the two lines correspond to the two limits that are here, and this line simply is the Ledoux limit. So below this line, it is unstable, the fluid is unstable to overturning convection, and in this regime it is unstable to fingering convection, where it is thermally stably stratified. And as you move more and more towards the marginal stability, where these two ratios, these two diffusivity approach each other, you get this other limit of fingering convection. So in this regime is the interest of study of this instability in any astrophysical system. So how this study of astrophysics, of astrophysical fingering convection has been revolutionized over the last years because of the developments in high-performance computing, which enables us to study these instabilities in very, very high-resolution 3D numerical simulations. And the very pioneering work of Justin Brown with Pascal Garot in Santa Cruz studied this instability in at very astrophysically relevant parameters for the first time, and gave us a very exciting result with respect to the transport rate or the mixing that occurs due to this fingering convection. So typically we quantify the mixing in terms of the Nusselt number, which is simply related to the turbulent diffusivity and the microscopic diffusivity in this way. And if you see this plot, this illustrates the onset of the fingering convection, where this compositional and thermal Nusselt numbers are plotted as a function of time. And you can see that for the fingering convection regime, you get a very significant enhancement due to fingering convection, as is illustrated by the Nusselt number values in this plot. So the Nusselt numbers for the composition is much, much greater than unity for fingering convection, which means your turbulent diffusivity is much, much larger than the microscopic diffusivity, and here you get a mechanism for efficient mixing. Whereas the thermal Nusselt number always stays around 1. So fingering convection never transports heat, but it's efficiently transporting elements. So what the Brown model, study was special for is that they not only did 3D direct numerical simulations for realizable parameters, but they also proposed a model where you can extend this, the domain of study of these 3D simulations towards astrophysically relevant parameters, which are often not realizable in numerical experiments. So what how their model works is that they propose this turbulent diffusivity in terms of the basic growth rate of the finger instability, which is lambda, which you can directly come up from basic linear stability theory, and the wave numbers of your growing modes. So this relation they calibrated with the help of numerical experiments. And just I want to mention that this basic linear model of this instability is based on the fundamental idea of Ratko and Smith, where you propose that the fingers which grow in this simulations and become turbulent and grows to a very steady saturated state, in that growth phase, the secondary instability between the fingers, which occurs due to the shear, is simply related to the basic growth rate by one constant. So this is the basic assumption of this model, of the Brown model, and this works remarkably well for all the realizable set of numerical experiments that they fitted their model with. So this plot shows the composition Nusselt number as a function of the reduced density ratio, which is just defined as this. So you can just take it as a measure of stratification in the fluid, and you can see that the Brown model that I described in the previous slide gave us fits which agree remarkably well with this with the numerical experiments that they carried out, which are these points. So we have a reason to believe that this model works, that simplistic model works for a wide range of fluid parameters. And this is what enabled the Brown model to make predictions for astrophysically relevant parameters, which are this Prandtl and tau, that are asymptotically small in stars. So with this framework, they studied a number of astrophysical cases of where this fingering convection is proposed to occur. And I would the first study I would briefly describe is with respect to the outer envelopes of low mass stars, where you can get some iron-rich layers in the outer atmosphere due to radiative accelerations of the iron element from the outgoing photons inside the star. So and it is competing against the gravitational settling inside the star in the outer layers, which occurs here. So when I play this video, you could see the rapid onset of the fingering instability in this iron-rich region, where these typical finger-like structures are protruding. And you can actually model this with the help of the Brown model very well and account for the dilution.
Iron accumulates there in the first place?
So this occurs due to radiative acceleration. So you have absorptions of photons by the iron lines in the outer atmosphere of stars, and this is.
But where was the iron formed? Did it form in the core and migrated all the way?
No. It's just a primordial iron. So this is a low mass star. It has just primordial iron in its stellar atmosphere, and this gets kicked due to the photon. From the incoming photons from the interior of the star. So as they propagate outward, they impart kicks, and this is very dependent on the mass number. For iron, the radiative acceleration is very efficient in stellar.
So you start with a primordial content of iron,
yeah,
and you have photons that bring it all the way to the edge.
Yeah.
Why does it stay on the edge?
Like
you had photons. Photons were strong enough to push it all the way to the edge.
Yeah, right.
Why isn't it ejected from the star?
I mean, there will be stellar winds, but they're in low mass stars. It's only going out at a very small rate, right?
If it's strong enough to get it, what's strange to me is that.
But there is also competing effects at the surface effects, like gravitational acceleration and other stuff, and there's an equilibrium.
My point is that there's nothing special that happens with the surface of the star. Why would the acceleration stop there?
I mean, it's just the radiation that's driving there to the surface, right? Yeah. There's an opacity peak in the outer layer of the sun, and that's what determines this acceleration, the amount of accelerations. So that's how these models are very detailed and take into account all these atomic physics details. So you get this equilibrium between radiative acceleration and gravitation settling, and you can get this accumulation of iron. And that is what triggers this instability in the first place, because you get a compositionally heavy material on the surface above hydrogen, basically hydrogen. So this is a very idealized problem that had been studied without the effects of Fingering convection, and the Brown model gave us a way to study also with first 3D results that are fitted to the Brown model. Yeah?
Do you have both the
Sorry.
turbulent mixing due to this fingering convection? But in the meantime, you also have a preferential acceleration of iron.
Yeah, right. You get a uniform mixing of the Fingering convection because it's very efficient in this compositional mixing.
It's faster.
It's very fast.
Faster than the radial acceleration.
I mean, you have to think it in terms of a turbulent, a diffusive mixing scheme, and in that regime, it's like efficient with respect to like all the elements put together that goes into a mu gradient, right?
Well, I can't see how it's faster than the radial acceleration, because ideally, initially, the radial acceleration peaks rapidly.
Yeah, right.
So how can you beat that?
Once the instability kicks in, it's very efficient. So it's always competing against gravity, that's right. Like radiative acceleration is competing against gravity. But once you kick in the instability, it rapidly mixes the region that is unstable. It's how also convection works, right?
Well, I can't see how it can.
So if you have a convectively unstable region in this layer, it would also mix the whole region, right?
Let me just ask, so the radial force is included in the equation of motion?
Yeah, right. So you evolve the equation of motion of each element, taking into account all the forces, and the Fingering convection is just counted in a diffusive model that is given by the Brown. Moving on to the case that formed the primary motivation of my study with respect to rotation is the case of red giant stars. So a prime example of where Fingering convection is also supposed to be very efficient is in the deep interiors of red giant stars. So as stars evolve around the red giant branch, you get the typical luminosity bump in the upper RGB, where you have this is illustrated in this cartoon, where the stellar envelope penetrates deep into the interior of the star, and you get this discontinuity in the hydrogen, in the mu profile of the star that has been already smoothened by the penetration of the convective envelope. And at the same time, you have increasing growing inert helium core due to shell hydrogen burning. And once this inert helium in this shell burning region enters this mu discontinuity left by first treasure, you get an inversion in the mu profile, as is illustrated in this plot. And this is unstable to Fingering convection, because in the same way that I illustrated. So this inversion in the mu gradient is very tiny, but it's still unstable to the basic fingering instability. And what this implies is that the shell burning region gets connected to the outgoing, the receding hydrogen envelope, and this could bring materials of hydrogen fusion onto the surface of the star. So while this is just a picture showing, there is actual observational evidence for this that has been collected over data over a number of years. And still I show this old plot from Graton et al. Data, where you see the stars distributed, the composition of the star distributed as a function of luminosity, so it's proxy for stellar age. And you see the decline in the abundances of various elements and isotopic ratios on the upper RGB, where it has already crossed the stage where the convective envelope has reached its steepest extent. So if there were no additional mixing in this phase of stellar evolution, you wouldn't expect this decline, but you just expect this decline. And this is illustrated not just with one sample of data, but over a wide range of metallicities and stellar environments. And this seems to be a real case of are at something missing in this phase of evolution, which we think could be attributed to fingering convection. This is another set of data where you have some prescriptions for fingering convection, and you get this stellar evolutionary predictions for these abundances, and you can see that if you vary this efficiency of mixing with fingering convection, you can get closer fits to the observed decline in the abundances of this star on the upper RGB. So,
so you have fingers of heavier elements climbing up
from the base of the hydrogen burning shell
to the
surface and against gravity, because this has been basically homogenized due to fingering convection, and it connects the stellar envelope where there's constant convection going on to the hydrogen burning shell. So you have a continuous transport of elements from the deep interior of the star to the surface. Pardon?
It works against gravity, right?
Yeah, just convection does. Right? Convection mixes the entire star, right?
Right.
So it's the same way that it occurs. It mixes the entire star. It's turbulent.
To equate the entropies.
Yeah, exactly. As convection works. Only the time scale is different. So the time scale of this mixing is much slower. But that's where the crux of the problem lies, is to get the right rates of this mixing to match this data. And that's where the whole problem has been lying in this area of modeling over many years. And I will try to motivate why I want to study rotation in this aspect.
Clarify.
Yeah.
It's the gradient composition of what?
Of chemical elements, of all chemical elements. So you have a mu inverse.
The hydrogen stuff on top is lighter.
Is lighter, yeah. And you have nuclear processed elements in the shell burning region of the star, so that increases the molecular weight. So you get an inversion in the molecular weight profile due to the burn. So the inversion actually happens because of, in this case, it happens due to one of the nuclear reactions in the PP chain. So I can write down somewhere. I don't know if you can see. Here. This inversion actually happens due to the helium-3 plus helium-3 nuclear burning reaction that generates helium-4. So in this process, you get a decrease in the mean molecular weight of the star, because you have effective molecular weight decreases in this reaction. You have more particles that are participating in the reaction that are produced. So due to this particular reaction, you get this inversion in the mean molecular weight of the inside the star. So this particular reaction is what is essential for triggering this instability in this RGB stars. In this reaction itself, the mean molecular weight of the chemical species decreases, because you have two nuclei producing. Did I get this right? 4. Yeah, because it's proton. Yeah. So if you calculate the effective molecular weight, this decreases during the reaction. Oh, okay. So sorry, I should have mentioned that too. Is because this has to do with the edge of the hydrogen burning shell, because this reaction is triggered by the hydrogen burning shell. So you need it occurs right at the edge of the hydrogen burning shell in the red giant stars, and there is where the inversion in the mean molecular weight occurs. So you need the right temperature to trigger this reaction, and that is why this is quite fortuitous that it exactly happens at the right place in the star where this reaction is most effective. So at the edge of the hydrogen burning shell, you get this mean molecular weight inversion. And that triggers the fingering instability, which then homogenizes the entire radiative zone below the convection zone, and that transports these elements then to the surface of the stars.
This diffusion is on top of the rapid convection?
Yeah, it's on top of the rapid convection. So that's what this cartoon suggested. So that you have rapid convection going on in this area of the star, but if that was all, it wouldn't have mixed in this radiative zone that is separating the hydrogen burning shell and the outer envelope. So it is necessary to connect the hydrogen burning shell to the outer envelope through some mixing mechanism that can then transport these elements up to the rapidly convecting envelope. So this was actually proposed almost 12 years ago by Peter Eggleton first time, where they actually had 3D simulations of this hydrogen burning shell in very large facilities doing 3D simulations of reactive burning inside stars, and there they actually observed this finger-like structures where they proposed that this could be the mechanism that is triggered due to these burning reactions.
Well, the thing that's confusing a little bit is that the base of the convective envelope is separated from the hydrogen burning shell
Yeah.
by rather tenuous mantle.
It's a radiative zone, basically.
If it was a thin radiative,
It is thin radiative zone.
which is however geometrically not very thin.
It's not very thin. So if you measure it in radius, if it's measured in radius, it's quite
You're triggering this fingering in the hydrogen burning shell itself.
in itself, yeah. And that inverse mu gradient actually propagates outward till the base of the convective envelope, because the fingering mechanism is continuously smoothing that region,
Okay, thanks. Okay.
right? So this was first proposed in this paper, and that has been studied subsequently by in many models. But this is not the only mechanism that has been proposed in literature to achieve this mixing that connects the two regions, because these two regions are also separate. The radiative zone I'm talking about is also separated from the hydrogen burning shell and in a layer where there is strong shear between the different layers of the star. So it could also be very unstable to shear instabilities, and rotational induced mixing has been long proposed to also as a mechanism to transport the elements in this radiative zone. But in these studies, they always seem to predict mixing rates that are much, much lower than what is predicted by models of fingering convection. So the actual rates that are needed to match these observed abundance declines are not given by this rotational induced mixing. And so people also propose magnetic fields as is always done in astrophysics. And these studies also similarly seem to predict that it is not efficient enough to mix the layers and get the right kind of mixing rates to work over a number of abundances. Especially elements like lithium is very sensitive to this kind of mixing mechanisms, and where though the issue on this is still not well resolved, because there are no numerical simulations in this of magnetic fields that we could actually believe to work as a mechanism here. And lastly, and what has been studied most recently was in the group in Santa Cruz, where Pascal also studied the possibility of excitation of gravity waves in this regimes triggered by the fingering instability itself, whether you could have large-scale motions in this radiative zone that could also efficiently mix this layer. And the general conclusion of this study is that gravity waves, the excitation of gravity waves, is not a very suitable prospect for astrophysical regimes based on their numerical simulations only. So all these studies have been going on, and we seem to be missing some kind of conclusive picture in this regime that can consistently give us the right rates that are required by observations. And that was the main motivation that I had to investigate this problem. Before going there, just this is another cartoon that summarizes these problems that are occurring in the models, even by the Brown model, that are based on actual direct numerical simulations. And this is illustrated in this plot where you get the turbulent diffusive mixing rates according to the Brown model, and this green curve shows that the rates that are actually required by observations to fit the observations. And you can clearly see across a wide range of stratification, which is denoted by the density ratio, you do not reach to the values that are required by orders of magnitude. So we are missing something that is like crucial to explain this gap if fingering convection were the agent for mixing in this problem. So the need for a mixing mechanism to enhance this rates by orders of magnitude is what motivated us to propose rotation as a possible agent. And the idea is very simple. Comes from the classical Taylor-Proudman idea in fluid dynamics, where rotation always stabilizes motions, and you get an invariance of the flow along the axis of rotation. And this is like briefly illustrated in this numerical simulations, where you get basically invariant fingers along the axis of rotation. So my axis of rotation here is just along the z direction, and if you have fast rotation, these fingers actually just become invariant along the axis of rotation, and they don't shear against each other. That actually leads to the saturated turbulent state that quickly. So this is what is briefly explained. What happens is that the Coriolis forces make the fingers more coherent, so as is seen in these pictures, and it leads to a reduction of the shear instability that saturates them in the turbulent state. The fingering velocities then can grow to much higher values. So the flux that is transported downwards is higher, simply because the fingers themselves can move faster downwards. And this should naively lead to an enhancement in the mixing if you add rotation to this setup, right? But all this, does this all work in a nonlinear simulation is what we were interested in, because this idea is just based on the growth rate of the instability, and whether the fully nonlinear state will come up with an actual enhancement in the mixing rates was open to debate. So this is the only slide I promised to have so many equations, because this is what is required to go into the framework of direct numerical simulations, where we use the Boussinesq-model, as has been done in many scales of small-scale turbulence in astrophysics. So we have the divergence-free condition, and for a Boussinesq equation of state, where the two contributing terms of temperature and composition differ in a sign, so they are competing against each other with respect to their contributions to the density. We non-dimensionalize our units for doing our numerical simulations, and set up the 3D the Navier-Stokes in a rotating frame with the additional equations for the evolution of the temperature and the composition that give us this our Nusselt numbers for the mixing. And this non-dimensionalization is carried out with respect to these parameters, where we have the standard Prandtl number giving the ratios of the heat diffusivity of the viscosity to the heat diffusivity, the diffusivity ratio that is what controls the size of the fingers and the fingering instability. The density ratio is a measure of the stratification, as I described before, being the ratio of the temperature and the compositional stratifications. And we introduced the Taylor number, which is just a measure of the rotation, and it's just proportional to the square of the rotation rate. So in this framework of this of the rotating Navier-Stokes, we did a basic linear stability of this problem. Yeah, go on. This one, yeah. This is the 3D momentum equation. Yeah.
Why is the left-hand side multiplied by the inverse?
I mean, the inverse Prandtl is just the coefficient of the diffusive. So if you carry out this kind of non-dimensionalized, this equation can be recast in this way.
Did you non-dimensionalize P2?
Yeah, we non-dimensional P's appropriately in this framework.
You scale down the viscosity of the pressure and the temperature.
Yeah, right, exactly. So, so the basic linear stability of the problem, you introduce your perturbations, which are your basic fields of velocity, temperature, and composition in this normal mode analysis, where you have a growth rate with respect to time. And if you carry out the linear stability of the equations that I showed, what you get is summarized in these two plots showing the effect of rotation. So the left plot, you can basically see the picture that happens in basically a non-rotating setup or a very small rotation rates, where you get this so-called k equal to 0, which are the so-called elevator modes that are the fastest growing unstable modes in your system. So the color coding simply denotes the growth rates lambda in this plot. So the bright regions are the fastest growing modes, and they are always the k equal to 0 modes. And moving on to the right picture, this is simply at a higher rotation rate, about 100 times the left one. And what you see that even at such high rotation rates, what you get is pretty much the same picture, where the fastest growing modes are still the k equals 0 elevator modes. So rotation does not actually kill the fingering instability itself. So basic linear instability is still there. And we wanted to then explore how this picture can be carried forward into a nonlinear regime. For the preliminary purposes, we just investigated the polar case. So in that case, our rotation axis is just aligned with the gravity. And in that setup, we studied our linear equations to come up with a measure of what quantifies rotation in our system. So in astrophysical literature, rotation is typically quantified in terms of the Rossby number. And the Rossby number is simply the ratio of the inertial forces to the Coriolis force. And in rotationally dominated system, the Rossby numbers is typically less than 1, which implies that rotation is dominant over advection in the stellar plasma. And if you remember my choice of a non-dimensionalization, where I introduced this Taylor number, what you can argue for is in a high Prandtl number regime where you have very viscous flows, that the Rossby number, if you define the Rossby number in the fingering case with respect to this basic diffusion length scale, the Rossby number simply goes as the inverse square of the Taylor number. So it's just proportional to the rotation rate, inversely proportional to rotation rate. But as you go to lower Prandtl number, which is very inviscid k limit that are of interest to astrophysics, you can rigorously argue that the Rossby number is also related to the Prandtl number and the stratification in your stellar plasma, apart from this inverse square relation for the Taylor number. And this can easily be then converted in terms of the standard Brunt-Väisälä frequency, which is n square, and this quantity then quantifies the Rossby number that are actually can be measured inside, for example, stars. So if you just know the Brunt-Väisälä frequency inside the star, which is the buoyancy frequency, and the rotation rate and the measure of the stratification, you can come up with numbers to see whether rotation is actually dominant in your regime, in your astrophysical site of interest. So now with our picture of the RGB stars in mind, we have now, thanks to Kepler, we have actual data for RGB's rotation rates that I illustrate with this plot from the de Heuvel's Kepler paper, where you have measures of the rotation rates for the core and envelope of red giant stars. And if you do a more or less rough estimate using this relation to come up with Rossby numbers in these RGB stars that we are interested for fingering convection, you get a Rossby number range which lies quite from like rotational dominant systems to like very not rotation dominated system. So we had a motivation from the observational data that rotation could actually be very important for some, at least for some of the RGB stars. For example, the upper RGB stars, which have a stronger shear layer in the radiative zone, could have significantly low Rossby numbers if you go by at least the core rotation rates, which are a closer proxy of what is going on in the deep interior. So motivated by these numbers, we then carried forward to do a set of numerical simulations where we basically focus on the lower half of this parameter space. So I would like briefly describe what is the framework we used for our numerical simulations. So this framework relies on a very well-tested code that was developed by Stefan Stelmach in UC Santa Cruz to study a wide range of double diffusive problems, not just fingering convection, but also oscillatory double diffusive convection in the ocean and in normal environments like geophysics provides us, as well as in astrophysics. This was extended by the thesis of Adrian Traxler, who actually provided asymptotic scaling laws for astrophysical parameters for the first time. And this is a code which is very simple to use because it assumes a triply periodic setup in all three directions, and we start off with randomized initial 3D fields to study the growth in amplitude of these instabilities. This code was lately developed to study the effects of rotation in the semi-convection regime by Moll and Garot in this paper, and I further developed it to extend it to the whole parameter space of double diffusive convection to do high resolution numerical simulation of rotating fingering convection. So a typical run of our numerical simulation doesn't require very high resolution, but it is very illustrative of the basic effects of rotation in the evolution of the fingering convection. And as I argued in the previous slide, we chose to study a parameter regime which is relevant for a problem of interest, which are the RGB interior. And for our DNS, we used a very quite a low Prandtl number that is not near as low as astrophysical regimes, but it is still enables us to study fully resolved direct numerical simulations of rotating turbulent convection.
This resolution is sufficient.
So this is subject to many direct numerical simulation experiments where you figure out whether your smallest scales are resolved fully in this simulation. So you have to look into the early development of the instabilities to gauge out what is the appropriate resolution and that this is very dependent on parameters. For example, the Prandtl number, the Rossby number, this actually go into determining this resolution. So I just denoted that this is on the average just sufficient for resolving the scales for our range of Rossby numbers.
We have another concern here. So in this unit, one of the numerical artifacts is that you have artificial diffusion.
So
this is going to be something that's going to be most prominent when the resolution is low.
It will be, but it will be. You are exactly right. But in a spectral code, you can make that out very easily. So in a spectral code, if your resolution is not, it will just blow up. It will show weird, crazy features very early on in the simulation. So you can actually detect this in spectral techniques much more faster than normal like finite volume or finite element codes, because the spectral technique is very sensitive to this diffusion effects. So if you have unphysical effects, it's easier to resolve with spectral codes. But I mean, absolutely, you are right that you always have some diffusion, but if your resolution is high enough, your physical scales won't be that sensitive to that diffusion. It does.
The question is comparing the numerical diffusion
To the actual physical diffusion, yeah. So we rely because of the physical scales that are involved in the problem, and once you resolve those scales, you are happy with your simulation. And in our case, the basic length scale is this, the diffusion length scale, which is set by the diffusivity ratio simply. So once you resolve that scale in your simulations, you are happy that your spectral simulation is good. So we tested this for a number of cases to see the velocity profiles and other quantities, and we are happy with this distribution. So so as a summary of all my set of runs, I show this plot from this paper we just published that quantifies the effect of rotation on two different levels of stratification in our direct numerical simulations, where towards the right you have increasing rotation. So as you can, if you remember the basic Taylor-Proudman idea, you can readily see that this turbulent convection state, which is the nonlinear saturation state of the fingering convection, becomes more and more aligned as you increase, more and more coherent along the vertical direction as you increase rotation. And that pretty much goes into the picture that I was describing, and this is more and more evident as you go towards increasing stratification, where you actually see these structures line up. And these Rossby numbers, the corresponding Rossby numbers, are denoted in these bottom plots. So this is the very low Rossby number case, which you can see very clearly the effects of rotation. So what our next step was to extract the turbulent fluxes from these simulations. So the turbulent fluxes are, so the colors I should mention are just the vertical velocity field. So the bright colors are the higher velocities. So here is like the crux, the surprise part of the story is that when we actually extracted the turbulent fluxes that I quantified in terms of the Nusselt numbers from our direct numerical simulation by measuring the fluxes like the temperature and composition, and plotted it as a function of the Rossby number that we used for our simulations, we found over two orders of magnitudes in Rossby numbers that are relevant for our problems of interest, that rotation always seems to have stabilizing effects with respect to the non-rotating turbulent flux predictions that were studied by the Brown model. So these horizontal lines simply are the non-rotating flux values, and you can see that all the rotating runs seem to saturate to a state that is significantly lower than the non-rotating flux predictions. So this was like counterintuitive and goes against our proposed mechanism for enhanced turbulent fluxes in fingering convection by addition of rotation, and we were pretty puzzled and at the same time disappointed to see that in a turbulent regime, rotation seems to not enhance the fluxes.
This is also along the rotation axis, right?
All the simulations here are only in the polar axis. It can be completely different, as I will mention towards the end of our talk, if you go to our off-axis case. And there have been simulations done in the oscillatory regime for the off-axis case that seems to suggest that this general picture where you don't get an enhancement seems to work, even in non-axis, though the geometry of the problem is very different. Right? So all this story was not really fitting in our picture of RGB enhancement in fingering convection, but we always were worried that whenever you add rotation to your simulations, you introduce an extra time scale in your problem. So that's a rotation time scale, and we were always worried that what happens if we run our simulations for longer that are much beyond the diffusive time scales, but more towards the rotation time scale, to see there are longer term evolutionary effects of rotation on these simulations. And one such simulations that I carried out for a significantly longer time. So this is illustrated in this plot, where this is the typical diffusion time scale in our problem, and I integrated this problem about this particular run for about 6 times longer. And I would play the movies one by one, starting from the left, where you see the onset of fingering convection in this domain, And as you let it evolve over a much longer time scale, what you happen to see that this turbulent convection always gets reorganized due to rotation into this strong coherent vertical columns, which are cyclonic, so co-rotating with the rotation of the domain. And if you run it even longer, what happens is these small coherent structures that you can easily see actually align themselves and merge into one large-scale structure in your domain. And this is a feature that has been not only studied by in the framework of double diffusive convection, but also in turbulent Rayleigh-Bénard convection, rapidly rotating Rayleigh-Bénard convection, where you also observe this large-scale patterns emerging, and in all those cases, the cyclonic patterns always dominate and emerge very strongly in your numerical simulations. So why this was any of interest to us was that if you integrate these runs and come up with such large-scale structures in your simulations, what would be the effect on the transport rates? Would you get an enhancement compared to the small-scale turbulent features that are there in rotating fingering convection? And the answer is a very positive one, and as you can see in these simulations, where I also plot the Nusselt number as a function of time in this evolution, and you can see the Nusselt numbers initially saturate and then drop due to this reorganization phase, and then continue to rise and almost saturate to a value that is much, much larger than normal runs that I integrated for a considerably less amount of time. So the rotation seems to have an effect on a much longer time scale than the simple diffusive time scale that is important for fingering convection, for the structure of the fingering convection. As I mentioned, sorry for this, the Rossby number of this particular simulation that I studied over larger time scales was actually in a regime that has already been proposed to be very typical of the emergence of these large-scale structures, at least in rotating turbulent convection, as was studied in this paper. And their results are very reminiscent of what we observed in our simulations with respect to feedback of energy from small scales to large scales. That is exactly the inverse of what happens in turbulent convection, where you have the direct cascade of energy from large scales to small scales. So these simulations were very encouraging and led us to the idea of investigating this in the framework of this general picture of turbulent rotating convection. I also, before going into that, I also show you a snapshot of the fully turbulent regime of this simulation that showed the large-scale vortex emerging. And you can see in this features that in the core of this large-scale vortex, you have a high concentration material that is being advected downwards, and that is what gets your flux values to such high order, like orders of magnitude higher, because you are concentrating very high concentration material at the core of your large-scale structures that is very efficiently being transported by the vortex. So the scale of this vortices always depends on what domain you choose, and these are parts that have already been studied in context of rotating Rayleigh-Bénard convection, and we also plan to do such studies to see how large these vortices can grow to, and how dependent are they on the domain of our study. So as I was saying briefly, that the theory that goes behind the study of this emergence of these large-scale structures goes back to the notion of that Zeman proposed with respect to coming up with a length scale that determines this transition from of the feedback of energy from small scales to large scales, which is the so-called inverse energy cascade. So this is illustrated in these two cartoons where I have marked the so-called Zeman scale, where the rotation rate is such that it is the inherent length scale is imposed by the rotation, where the local vorticity becomes the same of order of magnitude to the rotation rate. And you can easily translate this in terms of the Rossby number or the Taylor number. And this actually happens around when Rossby numbers become of the order of unity or lesser. So this is the case that is illustrated here, where the Zeman scales is larger than the typical length scale of fingering convection, which is denoted by this. And in that case, you have sufficient energy that is being cascaded down into the smaller scale turbulence, and this is the direct energy cascade. But if you have the reverse situation where your local vorticity length scale becomes greater than the typical energy injection length scale, which is the fingering length scale, your direction of energy cascade is reversed, and you have a component of your turbulent energy going to feed this large scale vortices. So this is the general picture that has been there in literature for decades now, that this inverse cascade is effective and is only controlled by your energy injection length scaling problem. So it's not surprising if you vary the rotational parameter, we will approach a regime where these two become comparable. And that's what we proposed is happening in the prana you showed, where you hit this regime where these two length scales become comparable. And what is interesting is that whether this regime actually is relevant for stars, for the RGB stars. And in that aspect, if you remember the number I showed, I don't know where it went. So this Rossby number is not that low, or not is to be out of the regime of RGB stars at all. So the observed, the inferred Rossby numbers from the RGB Kepler data, which we believe to be in the range of 0.05 to say 5 or 10, is very much in this regime. So you could very much end up with these conditions where the inverse cascade could be efficient. So so this is the last plot about this, which actually quantifies this inverse cascade in terms of the energy spectrum in our simulations. So in our simulations, that are denoted by these two time snapshots of the simulations plotting the horizontal energy spectrum in terms of the horizontal wave numbers. And you can see that you can see very well a shift of this turbulent energy spectrum to steeper values as you progress into this large-scale vortex features. So this is also a feature that has been observed in turbulent Rayleigh-Bénard convection, where rotation actually steepens this energy spectrum as you end up with large-scale features. So this general picture of rotating turbulent convection seems to be reinforced in terms of the regime that we study in rotating fingering convection. And that's why we believe that this is actually a real effect. So I have been always arguing for this as an efficient mechanism, and it seems that we have actually unearthed an efficient mechanism to get our mixing rates right. But there are many caveats to this, which I would propose as open questions in this part of the talk. That I said that this LSV mechanism is effective at certain parameter regimes, and this just goes into the Rossby number, which is related to the Prandtl number in our simulations. But these Prandtl numbers are very far off from real astrophysical regimes, right? So one open question is that whether this would actually hold as we decrease the Prandtl number. And this is what I am actually doing in a part of an ongoing study that we are looking to come up with some kind of scaling for these Rossby numbers that are favorable for large-scale vortex formation, and see if they have any hint of a scaling with the Prandtl number, and whether that would indicate that as we go asymptotically to our astrophysical Prandtl numbers, these Rossby numbers would actually go down or go up by a lot. So that would be important to see that whether they fit in the regime that is inferred from Kepler observations for RGB stars. So that is one part of the picture. Also, another part of the picture is that the timescale argument that I was giving, that you always have some kind of time scale imposed by a rotation rate and whether the LSV evolution time scale is comparable to that. And that would be determining how efficient they are on the upper RGB, because these RGB stars are very rapidly evolving on our time scale. So the dependence of LSV properties on Prandtl numbers are also what I'm going to investigate in this study and come up with the transport rates at lower Prandtl numbers. So that is a natural progression of this work. A point that I briefly hinted towards is the dependence of these simulations and these predictions on the domain size or the aspect ratio of our box. So you often have these studies that see these vortices come up, but when you change the aspect ratio of your box from a non-square to something more elongated like a rectangle, you rapidly see these vortices transition into jet-like features. So that is a feature that is particularly predominant in studies of Rayleigh-Bénard convection, and in those cases, whether these jets would also enhance mixing rates is something that is not known for fingering convection. But there are hints that that is the case for Rayleigh-Bénard convection at least. Also, as you mentioned very pertinently, that all these things cannot possibly hold in the same way for a non-polar case for off-axis simulation. So that's what has been studied in the study by Ryan Moll in the oscillatory regime, where you get these jets forming, and I would just simply say that this enhancement picture seems to hold even if you have jets forming in an off-axis case. So I would like to quantify that as a function of the latitude, for example, in our simulations, but that is subject to future work. So I'm almost out of time. So I would also say that the RGB is not the only case where we think that fingering convection is an efficient mechanism. It has long been proposed that these main sequence events are also prime candidates where you get a mean molecular weight inversion, for example, during accretion events in low mass binary systems, or due to engulfment of planets, the close by planets in a stellar environment where there could be significant metallicity enrichments occurring due to this engulfment events. So this had been studied from the works of Sylvie Vauclair and also by Pascal, and these are all very subjective to the rates, getting the rates of the fingering convection correct. So once we believe there is some robust estimate for the mixing rates, we can come up with actual pictures, actual numbers for this kind of scenarios and the metallicity enrichments. And this has widespread implications for the theory of like planet compositions and composition of extrasolar planets, for example. This is more of a conjecture that I want to mention, that fingering convection has recently also been proposed in the case of resolving some long-standing puzzles in the brown dwarf community. For example, this study by Tromblin et al., this should be 2015, was actually refuted by the recent work by Jeremy Leconte, and there is it's very open to debate whether this is actually a mechanism at all in brown dwarf community. But coming to the large-scale vortex idea, these polar vortices are actually observed now in red giant planets, right? You have these polar vortices emerging in many planetary studies, like the famous pictures by Juno of Jupiter, and these polar vortices are occurring on scales that are unimaginable, and they are very robust features. So just a general understanding of the mechanism of these sustaining these polar vortices in this turbulent convection regime is something that of great interest to us, because we are interested ultimately to study what feeds these polar vortices in turbulent convection. And the last application I have in mind is the one I have been studying with a student of Lars Bilston from Santa Barbara, where he studied very recently. He had this paper in APJ Letters, where he studied the case of planetary, the accretion of planetesimals onto white dwarfs. And now you have this Kepler data of white dwarfs, where you also have the measure of the rotation rates, and we can actually now give them a prediction of whether the Rossby numbers are in the right parameter regime for our study not to affect their predictions. So their predictions are very much determined by what are the mixing rates that go into the calculations, and that in turn determines what are the slides of the planetesimals that they accrete on the white dwarfs, or also the accretion rate of these events. And another, maybe a bit far off application is that of thermonuclear explosions on white dwarfs. So you also have these kind of events that triggered the same burning sequence that I wrote down here, and this has also already been proposed as a method of digging up the white dwarf material and enriching the ejecta of classical novae explosions, for example. So this is another thing that is very sensitive to getting mixing rates right. So with this picture, I would like to thank you again for your patience and any questions you might have. Yeah, sure.
I think because of time constraints, we'll just have one question, and then we can continue the discussion.
Yeah, sure. Yeah.
So, do any of your results apply to Jupiter? Because I thought Jupiter.
So, yes, Jupiter is a case where polar vortices are seen, but we don't know what is the turbulent mechanism for the generation of them. What I described is only the case of fingering convection, right? And fingering convection is driven by a molecular weight inversion or some kind of chemistry going on the envelope. And we don't have that information for Jupiter at all. And we have no signs of expecting something weird happening in the Jupiter polar regions, which would trigger this kind of events. But in general, if you have some kind of shear flow occurring in planetary atmosphere that has some kind of vertical transport, we have a reason to believe that these vortices would occur.
I thought it was also occurring in the core.
People are. So Pascal herself has been studying the core, the diffusive erosion of the core of Jupiter due to double diffusive convection, but that is due to the so-called semi-convection regime of double diffusion. And that has also been studied with rotation by the study of Moll and Garot. So in that study, they didn't find rotation to be significantly affect the double diffusive erosion of the core.
So let's take Sutirtha again.